So if we begin to put together oxygen here, so if we look at where it's at on the periodic table, we have 6 valence electrons. And so we put those 6 valence electrons in here, and they look something like this. Now, what we want to do with this is we want to put those valence electrons around the oxygen. And one of the ways that I look at it is thinking of the oxygen having a square box around it, and we start to place those electrons around. So I go 1, 2, 3, 4, 5, 6. So we have our 6 valence electrons. Now you'll notice that we have 2 unpaired electrons. These actually become what we call bonding sites. And so really oxygen would like to have 8 electrons, but right now in its normal neutral state, it's missing 2 electrons. On the next screen we're going to start to look at, well, how do we match these things up with other atoms? So if we go back to oxygen and we realize oxygen is going to look something like this again. Notice I'm using Hund's rules to put in the electrons. And let's say we take hydrogen. So we got hydrogen here, we have oxygen here. And hydrogen has 1 valence electron. And actually there's no p's in the first energy level, so we could actually just scratch those guys out. Oxygen again, as we put electrons around it, I'm going to put both electrons on that side and then put these 2 lone ones over here. Now it really doesn't matter as long as we have those 2 lone electrons. Now if we put hydrogen up, hydrogen has 1 electron. What happens to create a bond is hydrogen and oxygen need to share. And you'll notice if I add a hydrogen here on the end of the oxygen, we get a bond. Now this pair of electrons represents the bond between hydrogen and oxygen. You'll notice that oxygen still has 1 lone electron. Hydrogen only has 1, so it can only bond once, and so what we have to do is we have to have a second hydrogen. And so we bond down here, and you'll notice now if we count all the electrons around oxygen, it's pretty happy because its valence shell looks a lot like a noble gas. So we have 1, 2, 3, 4, 5, 6, 7, and 8, where 2 of the electrons come from the hydrogens to bond. Hydrogen is in the first energy level, and hydrogen can only have 2 electrons in the first energy level. So you'll notice hydrogen's happy too because it's got its own electron plus it's got this one from oxygen to finish out that energy level. If we look at a variety of compounds, this first one, lithium fluoride. Lithium, if we look in the periodic table, and we'll scroll down, is in this first column. It's right here. And lithium, that means it has 1 valence electron. And if we look at fluorine, we look back up at F, fluorine is in the 7th column, making it have 7 valence electrons. So fluorine's missing 1 and lithium's got 1. So basically we start out, we have lithium, it's got 1 valence electron. And then what we're going to do is take fluorine and write all of its down. So we have fluorine, and then you have 1, 2, 3, 4, 5, 6, and there's the 7th one. Now the odd thing about this, well, I guess it's not odd, but fluorine has a great attraction for those electrons. So fluorine actually kind of steals this electron from lithium, and fluorine becomes negatively charged and lithium becomes positively charged. It's actually an ionic bond. If we go over to magnesium and bromine, magnesium has 2 valence electrons, and so we start to write them. Here's its 2, there's 1, 2. And then bromine, again, if we look in the periodic table, has 7 valence electrons. And so we come in here and we start out and go, whoops, this is bromine, not fluorine. Bromine, 1, 2, 3, 4, 5, 6, 7. And notice bromine only had 1 to bond, so we need a second bromine to bond on the other side of bromine or magnesium. So we finish this one out. You'll notice now bromine sees 8. Magnesium's kind of odd though because it only sees 4. But again, this is an ionic bond. You're taking a metal and nonmetals and bonding them together. And so bromine becomes negative because it captures this magnesium's electron, and this bromine becomes negative and the magnesium becomes +2. Aluminum's going to be really similar, but if we get to nitrogen, nitrogen is a nonmetal, and so is chlorine. So when these guys start to bond, what happens is we got nitrogen with these three lone valence electrons. It's got 5 valence electrons total, but it's got those 3 lonely ones. And if we come in with the chlorines, chlorine has 7, and you notice it says Cl3, and the reason it says Cl3 is because chlorine only has 1 available bonding site, which is right there. And so we need 3 more of these chlorine to finish off nitrogen, so it goes to 8. And there's our 8. And you'll notice chlorine has 8, nitrogen has 8, and everybody in the whole Lewis dot structure is satisfied. There are cases where we'll go beyond 8, or a lot of times we'll say we'll violate what's called the octet rule. But for the most part, probably 80% of the time, we'd like to get to 8. We want to have a full outer shell. So if we get to methane, CH4, carbon's going to have 4 valence electrons, so that means it has 4 bonding sites. So we come in here and pick a pen. We put a hydrogen here. There's 1 bond, 2 bonds, 3 bonds, and 4. When we get to propane, if you think about what's going on here, these start getting a little tougher to do, because what you have is you have 3 carbons, you got 6 hydrogen, and it's kind of like, how do I bond all this together? As soon as you put a hydrogen on something, it actually stops the molecule. You can't go any further past hydrogen. But if you look at our 6, say our 6 hydrogen, and we distribute them kind of evenly, I'm going to put 1, say there, 2, 3, 4, 5, and 6. So now we got a problem, because you'll notice that this carbon has 2 bonding sites, this carbon has 2, this carbon has 2. Well, we need to bond, we need to somehow bond these carbons up. And so if we go back and look at, maybe we'll make a bond here, and you notice I'm going to put a line in here, and that represents 2 electrons. And I'm going to put a bond in here. Okay, so we've eliminated one of the problems, but still we have 1 electron over here and 1 electron out here. So what if we came in, and we're going to see if I can erase something. What if we came in and erased this hydrogen? Now what we could do is we could actually bond these 2 carbons together, and we still have that 1 hydrogen left to deal with. So we come back, and I put that last hydrogen out here. So it's kind of like putting together a puzzle. You know, have we satisfied the need of every atom in the structure? You'll notice that we have all the hydrogens taken care of and the carbons. And so to pretty this thing up, you'd have a double bond between carbon and a single bond to that carbon, and you'd actually have 3 carbons around this atom, or 3 hydrogens, a hydrogen there, and 2 hydrogens here. Now, all the carbons needed 4 more things bonded to them. And so if you wanted to check to make sure, you know, did we satisfy that each one of them had 4? There's 1, 2, 3, 4. Count 1. We can go 2, 3, 4. 1, 2, 3, 4. So all of the carbons are satisfied. They have 4 bonds because they needed 4 things. In our next video, we're going to look at some other structures and extend our what's called the octet rule. So watch this second one, and we'll see what you've learned.